Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I will continue from the last class. Last class I was discussing chemical thermodynamics. Under that I was discussing important points of the chapter. That is the special attention, because all these points are very important for examination. Now I will further continue with important questions that is related to competitive examination for IIT, JEE, NEET and other competitive examination. Keeping in mind the competition, I am going to discuss now some important points of chemical thermodynamics. Actually, I am reviewing the chapter chemical thermodynamics, energetics and chemical thermodynamics. Now, again, I'm going to discuss that is a competition window. You can tell that is questions related to competitions for IIT and NEET exams. First point, that is calorie, joule and erg. How all are related? Calorie, joule and erg. Then here 1 calorie is greater than 1 joule and 1 joule is greater than 1 erg. Second important point, during isothermal expansion of an ideal gas, delta E is equal to 0 and delta T is equal to 0. In that situation, H is equal to E plus PV, that is delta H is equal to delta E plus P into delta V. In terms of change, you can write H is equal to E plus PV. That you can write delta E. Delta E is equal to delta H is equal to, in the place of H you write delta H. Then H is equal to E plus PV. Then delta H is equal to delta E plus P into delta V, because P is constant and volume is changing. And now already I told you that during isothermal expansion of an ideal gas, delta E is equal to 0 and delta T is equal to 0. Both are 0. Then now we have to apply that this condition you have to apply here. Then here delta E will be as it is. Delta H is equal to delta E plus P into delta V. Then now here you are going to make one change. PV is equal to RT, you know. PV is equal to RT. Hence now you can write, in the place of PV you can write RT. Then you will get delta E. Delta H is equal to delta E plus P into NR into delta T. N is the number of moles. For 1 mole, PV is equal to RT. But for N moles, PV is equal to nRT. But here T is temperature. Then temperature will change. Delta T. Okay. But here for isothermal expansion of an ideal gas, delta T is equal to 0. Hence entire term P into nRT delta T will be 0 and delta E is also 0. Two conditions were there. Delta E is equal to 0 and delta T is equal to 0. So now in the equation delta H is equal to delta E plus P into delta V. delta E is equal to 0 plus PV is equal to nRT. Then T also you can write in term of delta T, because T may change. But here, according to the condition, there will be no change. Then delta T value will be 0. Then 0 into nR, that is 0, and P is also there, P into nR delta T, and delta T is 0. Hence, all are 0. Delta E is equal to 0, P into nR delta T is equal to 0. Hence, delta H is equal to finally 0. Hence, enthalpy remains constant. Question is asked. That's why I have discussed in details. Okay, during isothermal expansion means volume is changing. Then in that situation, enthalpy remains constant. Correct? Reason is that delta in that condition, internal change will be 0 when expansion is isothermal. Temperature will be also 0, internal will be, energy will be also 0, because temperature is not changing. Then delta E will not change. Now, next important point, for the same increase in volume for an ideal gas, work done during adiabatic expansion is less than work done during isothermal reversible expansion. Question is asked. Again, I am telling you, for the same increase in volume for an ideal gas, volume change is same increase in volume for an ideal gas, work done during adiabatic expansion is less than work done during isothermal reversible expansion. Means in case of adiabatic expansion, that will be less, work done will be less, and here isothermal reversible expansion it will be more. Means you are comparing in both condition. That is during adiabatic expansion it is less, and during isothermal reversible expansion it is more. You remember, in the case of adiabatic expansion, Q is equal to 0, means neither heat will enter nor it will leave. Correct? Now, next important point, the inversion temperature Ti of a gas can be calculated from van der Waals constant. Van der Waals constant is a small a and a small v. A small a is related to attractive force, and b is related to volume. Okay, both a small a and a small b are van der Waals constant. Then inversion temperature Ti can be calculated from van der Waals constant of the gas. How? Then relation is there. This relation is very, very important. Ti is equal to 2A upon RB. R is gas constant and A and B is van der Waals constant. Relation you remember. Ti means inversion temperature. A small I, T, and down a small I means inversion, and T means temperature. Then Ti is equal to 2A upon RB. Question is asked, you remember it. Now, next important point, some useful relationship of free energy change with other quantities. Now, I am telling you. First relation is standard delta G. Standard delta G, delta means change. Standard delta G is equal to minus NFE cell. E cell, okay. means EMF, E cell. Then here E cell and delta G both are related. Question is asked. Actually, in electrochemistry, this relation is used while solving the numericals. Delta G, that is the free energy. There is a relation between free energy and E cell, a standard E cell. Then how both are related? Both are standard. Standard delta G, that is equal to minus NF standard E cell. Then here N is equal to number of electron, F is equal to Faraday, and E is EMF. Correct? N is equal to number of moles of electron. N is equal to number of moles of electron or number of electron. Okay? Just you can remember like that only. But here number of moles of electron. N means number of electron also you can tell. Then here N is equal to number of moles of electron. Because you are using the standard condition, then you should tell number of moles of electron. But is the number of electron only in cell reaction. F is equal to Faraday and E cell is equal to EM of the cell. EMF, electromotive force of the cell. Now, second relation I am telling you, that is the delta G, standard delta G is equal to minus 2.303 RT log K. Here K is equilibrium constant. K is equal to equilibrium constant. This relation will be applied when reaction is at equilibrium position. Then standard delta G is equal to minus 2.303 RT log K. Actually, it is ln, but ln now converted into log. That's why you have multiplied by 2.303. Then standard delta G is equal to minus 2.303 RT log K, where K is equal to equilibrium constant. This relation is also very important while solving the numericals. Now third relation I am telling you, that is also related to free energy. Then now that relation I am telling you that delta G at constant temperature and pressure, delta G at constant temperature and pressure means delta G you write in bracket and out of bracket you write in down T comma P, means delta G at constant temperature and pressure. T down T and comma P means at constant temperature and pressure. Okay, means free energy, standard free energy. Okay, not standard, only anytime. Free energy means minus delta G at constant temperature and pressure is equal to T into delta S total. T into delta S. Delta S means here change in entropy. This is the relation between free energy and entropy. Very less relation is there. Always remember. Now this relation is uncommon, not common. Okay, you should remember numericals you can solve either during calculation for delta E, delta G, or for delta S, entropy, for any you can say. In a system, when free energy is changing, that time also this can be used. When entropy change is there, that time also you can use. Then minus delta G at constant temperature and pressure is equal to T into delta S total. Delta S total. Okay. Then down S you write total, where delta S total is equal to what? Delta S total is equal to delta S of the system plus delta S of surroundings. Okay, delta S of system, delta S system plus delta S surroundings, that is called delta S total. You remember, total is equal to delta S of system plus delta S of surrounding, means change in entropy of the system plus change in entropy of surrounding. You add both, then you will get delta S total. That value you have to put in the relation, minus delta G at constant temperature and pressure is equal to T into delta S total. Next important point I am discussing. In the homologous series of organic compounds, enthalpy of combustion increases with increase in molecular mass, but calorific value decreases. Again I am repeating, this is important concept. In the homologous series of organic compounds like CH3, C2H5, C3H7, like that way, CnH2n plus 2, that formula you can use. Okay, either for alkane, alkene, alkyne, for any you can say homologous series, it will apply. In the homologous series of organic compounds, enthalpy of combustion, means delta H or H you can remember, enthalpy of combustion increases. Why will it increase? Because this molecular mass will increase, more number of carbon, hydrogen, oxygen according to the compound will increase. Correct? When it will burn, then it will release more heat. That's why enthalpy of combustion increases. Correct? Enthalpy of combustion increases with increase in molecular mass. Correct? But calorific value decreases. Calorific value decreases. Why? Calorific value also, that is the heat produced after burning, just like combustion. But here condition is there, per gram. Correct? But in homologous series, molecule 1 mole mass will increase, molecular mass will increase. More mass means it will give more heat after the combustion, because molecular mass will increase in series. Correct? But here in calorific value, that is the heat released by 1 gram. When 1 gram of any molecules, when it burns completely in presence of air, both here combustion also in presence of air, this also calorific value also in presence of air, but it must be burned completely, but only for 1 gram, not the molecular mass. That's why calorific value decreases of all this organic compounds in homologous series. Then you remember, in the homologous series of organic compounds, enthalpy of combustion increases with an increase in molecular mass, but calorific value decreases. Next important point, in the solubility of a substance, if the solubility of a substance is known at two different temperatures, the mean molar enthalpy of solution over this temperature range can be calculated. How? Then by applying you can say equations similar to Van 't Hoff equation relating to equilibrium constant with temperature. Again you listen carefully. If the solubility I am talking about, if the solubility of a substance is known at two temperature, suppose at 25 degree and 35 degree. You know that 25 degree solubility will be less and 35 degree temperature solubility will be more. Then these things you keep in mind. Just simply I give an example. Temperature may be others. Then if the solubility of a substance is known at two different temperature, the mean molar enthalpy of the solution, mean average, the mean molar enthalpy of solution over this temperature range can be calculated by applying equation similar to Van-Top equation. Van-Top equation means it is a relation relating equilibrium constant with temperature. Equilibrium constant with temperature. This is very, very important relation. What is that relation? Now I am telling you. Log C2 upon C1, that is equal to delta H divided by 2.303 R in bracket 1 upon T1 minus 1 upon T2, where C1 and C2 are solubilities at temperature T1 and T2. At T1, C1 is the solubility, and at T2, C2 is the solubility. Here you should remember that is the solubility and concentration is not 100% equal. Not 100% equal, but it is a close. Okay. Then C is also represented for concentration. Okay, but meaning is almost same. Concentration means number of moles present per liter. Number of moles present per liter. And solubility you can tell it per liter also, in gram per liter. That is the solubility. But here you can tell number of moles per liter, that is the concentration. Okay. Then sense is same. Then log C2 upon C1, that is equal to delta H upon 2.303 R, and in bracket 1 upon T1 minus 1 upon T2, because C1 and C2 are solubilities at temperature T1 and T2 respectively. Hence delta H can be calculated. Correct? Log C2 upon C1. C2 is knowing, C1 is knowing, and T1 is knowing, T2 is knowing. Then delta H easily can be calculated, because log C2 upon C1 is equal to delta H divided by 2.303 R. R is gas constant. Its value is also known. Correct? Now, next important point I am telling you, an adult requires how many calories, an adult how many calories per day require? This is very, very important question. It is asked in general competition also. And an adult how many kilocalorie per day requires? How many? Kilocalorie, not only calorie, kilocalorie. How many? Then you should know between 2500 to 3000. Between 2500 to 3000 kilocalorie per day. Remember this. 2500 kilocalorie to 3000 kilocalorie per day. Okay. Now next important point. When an element exhibits allotropy, the standard enthalpy of formation is taken as 0. You remember, very important condition. Correct? When an element exhibits allotropy, the standard enthalpy of formation, standard enthalpy H I am talking about, standard enthalpy of formation is taken as 0 for the allotropic form, which is most stable under standard condition, that is the 298 Kelvin and 1 atmospheric pressure. For example, in case of carbon has that allotropic form, graphite and diamond. Okay, then in case of carbon, delta H, standard delta H, F means formation, enthalpy change of formation, that is equal to 0 in case of carbon. Correct? In case of carbon, delta H, standard delta H, F means formation, that is equal to 0. For graphite it is 0, and not for diamond. Not for diamond, both are allotrop, but for diamond it is not 0. You remember, only for graphite it is 0. Similarly, in case of delta HF, in case of sulfur, delta HF, standard delta HF means formation, that is equal to 0 for rhombic form, not for monoclinic. Okay, remember, for graphite it is 0 delta H value, standard delta HF value, and for diamond it is not 0, it has some fixed value. And sulfur in case of delta HF value is equal to 0 for rhombic form, and not for monoclinic. Question is asked, that's why all this pointed I am discussing separately. These questions are very, very important for competition. Okay, now next point I am going to discuss the enthalpy change when 1 mole of the solute is dissolved in a definite number of moles of solvent, like 100 moles, 200 moles, 300 moles of solvent. How much you can say enthalpy will change? The enthalpy change when 1 mole, only 1 mole of the solute is dissolved in a definite number of moles of solvent is called integral heat of solution. Okay, it is not fixed 1 liter or this that. Fixed number of moles of solvent, whatever we, maybe 200 moles of solvent, 300 moles of solvent, but you are dissolving only 1 mole. Then it will vary according to the number of moles of solvent. Whatever we value, that is a different case. But that term is called integral heat of solution. The enthalpy change when 1 mole of the solute is dissolved in a definite number of moles of the solvent is called integral heat of solution. Next point, heat of ionization of a weak acid can be calculated by subtracting heat of neutralization of the acid with a strong base from 57.1 kilojoule. Here again you listen that for a strong acid and for a strong base, heat of neutralization, its value is fixed 57.5 kilojoule. Okay, then this is for a strong acid and a strong base. Heat of neutralization is 57.1 kilojoule. Correct? But if you want to calculate heat of ionization of a weak acid, then weak acid will not ionize full. Partially it will ionize. But if you want to calculate heat of ionization, because some heat will be used up in ionization, then that heat, if you want to calculate, then how we will calculate? Because numericals is asked, that's why I am focusing here. Then heat of neutralization of weak acid can be calculated by subtracting heat of neutralization of the acid, heat of neutralization of the acid with a strong base, okay, from 57.1 kilojoule. That is the heat of neutralization of acetic acid. Suppose it is a weak, it is actually acetic acid is a weak acid. Then example I am telling you, heat of ionization of acetic acid CH3COOH is equal to 57.1 minus 55.2. 57.1, that is for a strong acid and a strong base. Heat of neutralization 57.1. But now here heat of neutralization for acetic acid is 55.2. 55.2. Then actually it should be 57.1. But now it is a less, 55.2 in case of acetic acid. Then what happened? What happened? You can say this difference. Why it is 55.2? Why not 57.1? Then that difference 57.1 minus 55.2, that is a 1.9 kilojoule, that heat used up in ionizing the, you can say, hydrogen ion CH3COOH. Then as ion will ionize, it will give acetate ion plus H ion. For that heat is neutralized. Then this difference 1.9 kilojoule is used up in ionizing the weak acid. Likewise, heat of ionization of weak base also you can calculate from the 57.1 divided by any other, you can say, base, any other base like ammonium hydroxide, that is weak base. Then from 57.1, if you put the value of heat of neutralization of ammonium hydroxide, then you will get a difference. That will be heat of ionization of a weak base. That can be calculated. Now next important point, heat of neutralization of HF, hydrogen fluoride, is about 68 kilojoule. Very, very important questions I am discussing now. Heat of neutralization of HF, hydrogen fluoride, is about 68 kilojoule. That is more than 57.1 kilojoule. Because this is the for a strong acid and a strong base, heat of neutralization is 57.1 kilojoule. But heat of neutralization of HF is more than this, 68 kilojoule. How? Why? All should be maximum up to this only, 57.1. But why in case of HF it is a 68 kilojoule? Then this is due to very high hydration energy of fluoride ion. Okay, high hydration energy means actually HF, fluoride ion, is electronegative. Then it can attract so many H2O molecules. Correct? That time there will be, you can say, that heat will be involved. That's why heat will increase. Okay, they will make bond with water molecules. Then that time heat will be involved. That is called heat of that is hydration energy. That is called hydration energy. That's why its heat will increase. That's why heat of neutralization, because water molecules will be attached with F. Now if you want to separate all H2O, ionize H and F should be separate. Then H2O should also bond should break. Then that's why it will require more energy. That's why heat of ionization is more than 57.1 kilojoule. Now next important term, and that is actually concept I am telling you. Delta H combustion is always negative. Delta H combustion always it will be negative. Why? Because it will liberate heat. Heat will evolve. Okay, then heat of neutralization, heat of delta H combustion, change of enthalpy, always for combustion, in case of combustion, is always negative. However, now see, however, there are some reaction which involve combination with oxygen leading to partial combustion. Because reaction is taking place with oxygen, then you can tell it will burn. That molecule will burn if it will react with oxygen. That reaction with oxygen, actually that is called combustion. Then generally it is used for carbon, but not necessary always with carbon. Other also may be there, other molecule also may be there. Then some exceptions are there. Some reactions which involve combination with oxygen leading to partial combustion. But in this case, delta H will be positive. Delta H will be positive. Reaction will be combustion, but value delta H value will be positive. Example, N2 plus O2, 2NO. In this case, delta H will be positive. Delta H is equal to positive. Further, when F2 combines with O2, now reaction between fluorine and oxygen to form OF2. OF2. F2, fluorine and oxygen both react. Then which will, both are electronegative atom. Then now how both will react? Fluorine is a most electronegative. Oxygen is also electronegative. Then how will they react? Then here just a comparative. Fluorine is most electronegative. Then it will be treated as electronegative, and oxygen is comparatively less electronegative in comparison to fluorine. Then that oxygen will behave as you can say cation. It will behave as a cation, and fluorine will behave as a anion. Then oxygen will behave as a positive. Now fluorine as a negative. Oxygen behave as a cation. Positive means cation. It is comparatively. Oxygen is less negative, hence it will behave as a cation, and fluorine will behave as a anion, negative. Hence, O you have to write first, OF2. You can write OF2. Then F2 plus half O2. F2 plus half O2, you will get OF2, and delta H will be positive. These questions are asked. Now next point I am going to discuss. The compounds which have negative enthalpy of formations are called exothermic compounds. Exothermic reaction, you know, any reaction when heat will evolve, delta will be negative. That reaction is called exothermic reaction. But compound, then here same way the compounds which have negative enthalpy of formation, are called exothermic compounds, while those with positive enthalpies of formations are called endothermic compounds. One more point I want to discuss. The neutralization reaction of a strong acid with a strong base is, how will you write? In any strong acid, H will be there. it will release H plus. And in any strong base, it will release OH minus. Any acid, any strong acid, any strong base. In all strong acid, H plus, it will release H plus. And in any strong base, OH will be there. Then the neutralization reaction, what will happen? Only this reaction will be there, H plus OH minus. In any neutralization reaction of a strong acid with a strong base, what type of reaction will take place? Then H plus OH minus. Both should be in aqueous, in water. Then H plus aqueous plus OH minus aqueous, it will form H2O. Means water formation is you can say mandatory. Can a conform may necessarily H2O will form. That is the formation of water molecule. Correct? Then for 1 mole formation of H2O, how much heat is evolved? That is called heat of neutralization. In other way, for that during formation of H2O from H ion and OH ion molecules in aqueous solution, heat released during the process is called heat of neutralization. Correct? The neutralization reaction of a strong acid with a strong base is H plus aqueous in aqueous solution plus OH in aqueous, it will give H2O, liquid it will form. Okay, and delta H will be minus 57.1 kilojoule per mole, and in kilocalorie 13.6 kilocalorie. Okay, from this it may be concluded that enthalpy of dissociation, this is actually formation, then reverse is dissociation. Correct? Reverse of formation is called dissociation, breakdown. Then value will be reversed. Negative will become positive. From this it may be concluded that enthalpy of dissociation of water is plus 57.1 kilojoule per mole. Then now I am stopping only here. Next class I will continue with some multiple choice questions, important multiple choice questions based on chemical thermodynamics. Now I am stopping here. Thank you.